All right, hello, welcome. This lesson is going to be an example of modeling a situation that is periodic, a sinusoidal situation, and then figuring out what the equation should be, and using our graph and equation to solve a problem. So that's let's just dive in to a little sinusoidal modeling. Okay, so our learning objectives are to, given a scenario that a sinusoidal function would work for, I'm going to create a model for that, which is to create a function. And a model is basically just like a mathematical tool for predicting or solving problems for a scenario. And then we want to solve a particular problem with this model. So I'm going to list out some problem-solving strategies. These are like kind of like steps you want to think about when you're creating your model or coming up with a model. And the first thing to do is to try to build a graph of the scenario. So to take the scenario and tease out what are the different like important times and important values, and then to start plotting those. So you want to plot key values, like what happens when time is 0, or when you hit a period, and so forth, and use that to help build a picture, a graphical picture of what's going on. Once you've got the graph, it becomes 5 times easier, 10 times easier to actually create the function. To create the sine or cosine function that fits it. You've got your graph, you want to identify the max and min values from the graph. You can also identify this from the scenario, either way works. You'll want to identify the period, or how long it takes for whatever your periodic function is to repeat. So that's the time or duration it takes to repeat. And then the last thing you want to do is figure out what your phase shift is. And as I said, when you're doing these models, it's usually easier to choose cosine as your function than sine, just because cosine, all you have to do is worry about matching up a peak, whereas for the sine function, you have to consider finding a middle point that's increasing, and then shift it left or right so that one lines up. So for cosine, I'd say it's generally easier, though you can use sine. And then lastly, as a way to check your understanding, make sure that you actually graph the thing, graph it with Desmos, and see if it makes sense for your scenario. Like, does your graph fit the values that are described in the problem? And if it does, then hooray, yay, you're probably right. If it doesn't, then it's time to go back to the drawing board and reassess. Okay, so I would always test your graph just to make sure if it's correct. Okay, so here's our problem. This whole video is just going to be solving this one problem. We'll start off by framing what's going on. You have a pendulum that's oscillating back and forth. Oscillates means goes back and forth in a periodic fashion, so that its horizontal displacement fits a sinusoidal model. Let x of t be the horizontal displacement after t seconds. So this is the scenario we have. We have a pendulum which is just a string with a little mass, or, it's called a bob, attached to the end of the string. And it is going to be moving back and forth. So here's the furthest it is away at the maxima, furthest it is away from the middle at each of these maximas. And we want to figure out what x, which is the horizontal displacement after some amount of time, t seconds. So this distance right here is x. This distance right here. And now we have a choice. We have a choice to do. What is x equals 0 mean? Is that the furthest left it goes? Do we want to start x equals 0 here? Is it the middle, the equilibrium point? Do we want to start x equals 0 here? Or is it all the way on the right? That's a weird one, but it could be all the way on the right. Do we want it to be all the way over here? All right, so your choice, you choose where x is 0 is. I think it would be easiest to pick the equilibrium as 0. And then from that, we choose directions for positive and negative. So we'll say maybe to the right is positive and to the left is negative. So I'm going to go ahead and erase these other ones so we're not confused. We're going to say that x equals 0 is where the equilibrium point is. And if we go to the right of the equilibrium point, we're going in a positive direction. We're moving to the left of the equilibrium point, we're moving in a negative direction. Okay? So that's a choice, and I think this is the simplest one for this scenario. Initially, the pendulum is held at a distance of 5 centimeters to the right from the middle. So we can already start diagramming out what's happening. Initially, it's my eraser. Initially, we're 5 centimeters away. So this x distance from the equilibrium point is 5. And then after 0.6 seconds, the pendulum is at the other maximum. So we'll have swung all the way over here after 0.6 seconds. Just 5 centimeters to the left. So it looks like we're going to go 5 centimeters to the right, and then 5 centimeters to the left, and 5 centimeters to the right, and 5 centimeters to the left, and so forth. So we'll be able to start coming up with a graph from this. So our 3 tasks are to sketch a graph, and I said, you know, even if this problem didn't ask us to come up with a graph, that's where I'd begin anyway. So I went to sketch a graph displaying at least 3 periods or 3 cycles. Cycles. So a complete revolution, meaning back to the rightmost on the graph, or back to the rightmost maxima. I want to determine a function for x of t. So what function could I use to model the horizontal displacement after t seconds? And then I want to answer this question. What's the 6th time the bob is at the equilibrium point? So how much time has elapsed since we started for it to get to the equilibrium on the 6th time? So that's our particular equation, or particular thing we're interested in. Okay, so that's the whole problem. Let's go ahead and start graphing. Okay, so here are our axes. We have our axes are x up here. So that's different. Usually x is the horizontal axis. X in this case is our horizontal displacement, and t is the time. So x is a certain horizontal displacement after t seconds. Initially, the pendulum is held at a distance of 5. So what that tells us is, I'm going to kind of highlight this, 5 to the right. So x of 0 equals 5. And it's positive 5 because we're saying it's 5 centimeters to the right of 0. Remember, we said that 0 was the middle, so 5 centimeters to the right is plus 5. So we can start plotting this. We know 0, 5. Here's 5 up here. 0, 5. Okay? After 0.6 seconds, the pendulum is at the other maxima, which is 5 centimeters to the left of the middle. So we know this information. X of 0.6 equals negative 5. Because 5 centimeters to the left means we're in the negative part, we're left of 0, so we've got negative 5 as our horizontal position. So here's negative 5 down here, and we have 0.6, 0.6, so there's our other point. Okay, now from here we've got half a cycle. We've gone from the max to the min. So if I go another 0.6 seconds, so this would be 1.2, we'd be at the max again. And so we can see from this that the period is 1.2. So let's go ahead and sketch the graph. There's 1 cycle, and I want at least 3 cycles, at least 3 periods. So I'm going to go 1.2, and I can find 0.6 more as 1.8, 0.8, and then we can go 0.6 more, and that's 4, and then we can go 0.6 more, and that's going to be 3.0, and then 6 more, and that's going to be 3.6. So let's see, we got 2.4, it's here, 3.6 is here, so we've got, there's our graph. So that's 3 cycles, peak to peak, peak to peak, peak to peak, so we count 3 cycles right here, peak to peak to peak to peak. Okay, 2, 3. Want to determine a function for x of t. So what is x as a function of time? Well, we can see from this that cosine is a great candidate because we are initially at a maximum. So we don't have to phase shift the graph of cosine at all for this problem because it says starting at a maximum or starting at the furthest to the furthest to the right. That's where the bob is at 0 seconds. So our phase shift for cosine is 0. If we were to use sine, we would have to incorporate a phase shift. We could identify this increasing middle, which is at halfway between 0.6 and 1.2, which is, I believe, 0.9, and do a phase shift there, but that's more work. So let's be lazy and just use cosine. So our sinusoidal axis is 0. That's also nice. So y equals 0 is the sinusoidal axis. The amplitude right here is 5. The amplitude is 5. Here, I'm going to use a different color for this stuff. Let's use blue. So our amplitude is 5 because we're going 5 away from the sinusoidal axis. Sinusoidal axis is 0, y equals 0, because that's clearly the average between -5 and 5. And then the period is 1.2. So our period is 1.2. We've the sinusoidal axis is 0, the amplitude is 5, and the phase shift is 0. So phase shift. Okay. So from this we'll build the function. X of t equals 5 cosine of 2 pi divided by 1.2. I'm going to simplify this. 1.2 is equal to 6 over 5. So this is 6/5, which is 2 pi divided by 6/5. This is pi over 3, which is 5 pi over 3. Okay, because 2/6 is 1/3, and divide, divide by 6/5, you multiply by 5 over 6. So that gets 5 pi over 3. So here's 5 pi over 3. Whoops. 5 pi over 3. 5 pi over 3t. Note, it's important I'm not using x here. That's t, because not x. Because x is our dependent variable. It's the answer. It's the horizontal displacement for the bob. So we wouldn't want to use x inside of our function because our variable, our independent variable is t. So this is the independent variable. Independent. The x's in this case are dependent variable. 5 cosine 5 pi over 3 t plus 0. Done. This is it. That is the whole function right there. Quite nice. There is no phase shift and there is no vertical shift on this function. Okay, so there's our function. There's our. We're going to go ahead and answer this question. What is the 6th time the bob is at the equilibrium point? 2 ways to do this. We can do this graphically, and I feel like that's the easiest, is to do it from the graph. But if you were to try to do this, like what's the 20th time or something, then it becomes hard because you'd have to draw the graph for a lot of cycles to find the answer. So we're going to just find this graphically first, and then I'll show you a way to do it using a bit of algebra, but it's not too tough, the algebra. Equilibrium points, I'm going to circle them in, let's use yellow. So for this question, the 6th time the bob is at an equilibrium point, we have an equilibrium point occurring here, 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 and so forth. You keep going. So this is the 1st time, this is the 2nd time, this is the 3rd, fourth, fifth, and so this is the one of interest. That's the sixth time that it's at the equilibrium point, which is in the middle when x is 0. If I look at the kind of neighboring values here, we have 3.0. Sorry, it's getting hard to read now. So we have 3.0. Actually, I'm going to go to my next graph, okay, this is the graph of it, just plugged into Desmos. So this is the graph, this is y equals cosine of 5 cosine of 5 pi over 3 x. Right. So this is that graph plotted on Desmos, and we take a look. This is occurring at 1.2. I'll just highlight again which one we're interested in. So we're looking at 6 times. So there's 1, 1, 2. I'm not going to use yellow. Purple. 1, 2, 3, 4. So this time right here is happening exactly halfway between 3 and 3.6. 0.6. This is 3.0. Exactly halfway in between. That's 3.3. So to answer this question, it's just halfway between that valley and that peak. Halfway between these guys is the time when it's at the sixth time when it's at equilibrium point. Okay, so that's visually how to solve this problem. Pretty simple. You just count all the equilibrium points. You want the sixth one, and you know the equilibriums are halfway between the max and the min, and so that gives you that time. To do this algebraically requires a little bit more work and understanding of the solutions, or excuse me, the inputs where cosine is going to be 0. So let's go ahead and do this algebraically. So we want to know when it's equal to 0. So when is this equal to 0? Here, I need a little bit more space. Pause this. All right, now I've got a little bit more space. So let's go ahead and set this up. We have x of t equals 5 cosine of 5 pi over 3. And we are interested in solving this for 0. So when is this equal to 0? That's when it's at its equilibrium, remember? So what are all the answers? What are all the times when this is 0? Well, okay, so let's go ahead and divide both sides by 5. Well, that doesn't do anything because 0 over 5 is 0. So we still have, when is cosine of 5 pi over 3 t equal to 0? So what t's would satisfy this equation? So we think back to the unit circle, and when we think back to the unit circle, we would say, well, we need this argument, which is right here, 5 pi over 3t, to be one of these special values, either pi over 2 or 3 pi over 2, or we could keep adding and subtracting multiples of pi to this. So that says that 5 pi over 3t must be pi over 2 plus an integer multiple of pi. So any n would satisfy this equation. But we're going to be interested in a particular n, and it's going to be the sixth one. So just hold off on that for now. Just remember, this is the general set of t's that would work, that would make the cosine be 0. So if this argument, again, what's inside the cosine, is pi over 2 plus any multiple of pi, the cosine would be 0. Okay? So we set that argument equal to pi over 2 plus a multiple of pi. Now, we'll solve for t. So we'll multiply both sides by 3 over 5 pi, which is the reciprocal of that number. Multiply both sides by 3 over 5 pi. And so these cancel, and that gets us t by itself. T is equal to I'm going to go ahead and distribute the 3 over 5 pi through. So pi, I'm just going to be very explicit and slow in doing this calculation. Pi over 2, that's a 2, times 3 over 5 pi. So we note that there's a pi in the numerator and a pi in the denominator. Those guys get to cancel. 3 divided by 2 times 5, this is 3 over 10. So we get 3 or 0.3. And then when we multiply the 3 over 5 pi, so that multiplies this one and it multiplies this one, times the n pi, we see the pi's cancel and we're going to get 3 over 5n. Because those pi's cancel. So this gives us a set of solutions, set of times when the bob is in the middle, when the bob is at the equilibrium point. Our times are, we can start listing them out. 3/10. So I'll list them as in decimals. We have 0.3 as the first one, and then the next one would be when n is 1. So that was when n is 0. It says n equals 0. So now when n is 1, this is the next integer up, we would add 3/5 is 0.6, so this is 0.6. So we'd add 0.6 to that and we get 0.9. And then the next one, when n is equal to 2. This is going to be another 0.6 added on. Excuse me, not 0. Another 0.6 added on, and we get 1.5. And then when n is equal to 3, we have 0.1. And the next one, 4, we'd have 2.7. Next one, we have 3.3. 4. And we could stop here, but they keep going forever and ever because we have found the 6th time right here. 1, 2, 3, 4, 5, 6. 3.3 is the 6th time that our bob is at the equilibrium point. Okay, so this is a lot to look at right now, but just kind of backtrack and remember what were all the steps we did along the way. We set the equation to 0 because we were interested in the equilibrium point, so that was the first step. And then we divided and got cosine by itself, so we got cosine by itself. That was this step. We went to the unit circle, so here was step 1, here was step 2. We went to the unit circle to think about what are all the times, what are all the inputs where the cosine is 0. So this was step 3, and then we got here, we found that those times were pi over 2 plus a multiple of pi, and then we set that equal to the inside and solved for t. And that gave us a set of answers that we just had to figure out which was the one we wanted. Okay, so that was the whole process of solving it algebraically. We will be doing this process more in greater detail next week and the week after. So this is kind of just a taste of it. On the quiz on Friday, you likely can solve the problem just by graphing it. So just the technique I showed you of graphing. But this would be the way you'd approach it if you needed to find the 20th or 30th time or so forth. Since it's such a small it's not that far away from 0, it's easier. It's just as easy to graph it and find the answer. Okay, so that's the whole shebang in this problem. These problems can take a long time, but stamina is an important skill in solving math, and not giving up when you are stuck. Okay, so both stamina and perseverance are incredibly important skills to develop in math. And if you give up easily, then you will never go far in a lot of realms, okay? So you're learning 2 very important skills in this class of perseverance and stamina. Alrighty, I will see you guys on Friday. Have a good Power Justice Freedom Day tomorrow.